So again, this is section 7.5, graphing quadratics in vertex form. Okay, and we're going to talk about vertex form. And we talked about it yesterday, and it was at the top of your worksheet. That was that equation, y minus k equals a parentheses x minus h quantity squared. So again, vertex form.
Can you repeat that equation real quick?
Yeah, from yesterday. I'll write it at the bottom because we're going to write it anyway.
Y minus k equals a. Oh, I don't know. Why would you do the?
That's what we're going to do today. We're going to determine k, h, and a, and go over what everything means. Why what?
Why do you leave y1k and y2k?
And x1, h?
Yeah.
You know, that's a really good question. I'm curious also. I don't know. His question is, why isn't this just like x1 and y1? This looks like y minus y1 equals m times x minus x1 from linear form. But instead of m for slope, we have a now. Instead of y1 and x1, we have k and h, and it's squared because it's quadratic. So it's very similar to the form of point slope. Okay, of point slope form, where we had y minus y1 equals m times the quantity x minus x1. Anyhow, let's begin by taking a look at the graph. And you did this yesterday, that's why I'm saying this is as if you've never learned the lesson. I'm going through it. But here's your standard parabola over here on the right. Okay? And if we look at a table of values, we notice that all the y values are the squares of the x values. Everybody so far so good? 1 squared is 1. 2 squared is 4. 3 squared is 9, etc., etc. All right? Now, several things to point out here. First of all, there's an axis of symmetry. And symmetry means it's the same on both sides. And that axis exists right down the middle. And it happens to be the line x equals 0. Remember, your vertical lines are always x equals. And this goes through 0. So this is the line x equals 0. Which, in this case, is just the y-axis, right? The y-axis is the line of symmetry here. So the y-axis cuts this graph in half. All right, so we see the same on both sides. Second, the vertex exists at 0, 0 for this problem. What is a vertex? We haven't used that term yet in this class, but you probably heard it before. What is a vertex, right?
It's the point where the two ended.
Yeah, with a polygon, it was where the two corners met, right? So like a square has 4 vertices, a triangle has 3 vertices, it's where they meet. Well, the vertex in this case is this point right here. It's where the graph turns around. Another word for the vertex is the turning point. Okay? Another word for a vertex is a turning point. We can also classify vertices as minimums and maximum. So minimum, maximum, meaning this in case is a minimum. It's the lowest point in the graph. It's a min. If the graph had been drawn this way, okay, and it's delayed, there you go. The graph, if it drawn that way, it'd be a maximum. We'll talk more about those in the next section. And the last thing to notice is that the graph opens up. Thus it is, and write this down please, this is a calculus term you're going to use, concave up. Concave up. Okay? And all that means is that the opening is like this. Okay? And I'm using my hand to show you. If it were concave down, it would look like this. Okay? It would be a parabola that opens downward. That opens downward. So far, this should be pretty straightforward. Okay, now we're going to get into what our transformations are using the standard form, the vertex form of our quadratic. Okay, any questions so far? Good so far? All right. Slide now. Again, you don't have to write everything down like the words, okay? This is just wording. You don't have to write down the words at the top. What you're going to do is write down some conclusions. And you already have these from yesterday's lesson. Okay, a lot of this stuff you're seeing here is from yesterday's lesson. So what we're going to do first is take a look and say, well, what happens if the graph was y equals negative x squared? Or in general, if a has some value that is not just 1. The graph is going to change. So let's take a look at some examples of it. So here's what we're going to do. We're going to take a look at these examples here and make some notes on the side. First, this first example, the upper graph is our standard parent function. The blue is always going to be the standard parent function for all of these, okay? The blue. The red at the bottom here, this red here, let me dictate with the marker here, is negative x squared. So what can you say about the graph of a parabola when a is negative? what statement can you make about the graph of a parabola when A is negative? Jared? Good.
Do we have to use the word concave?
You could say it opens down, or you could say it's concave down. I would say concave down. Chris?
Can we just say it's a reflection?
Well, I won't say reflection because we're going to see later that it's a reflection when it's a parent function. But if there's some sort of a shift up and over, then we have to worry about reflecting and stuff. You could say it is a type of reflection, sure. But let's for now say that it's concave down. Okay? But yes, Chris, you're right by saying it's a type of reflection, but there might come a point where that can be a little tricky if you don't think of it the right way. So for now, let's say concave down. All right. Next, we have to look at the next two graphs to make another conclusion here. So look at this middle one here first, please. Look at this middle graph right here. And what we'll notice is that the graph of y equals x squared is right here. And then the minute the coefficient becomes a fraction or a decimal, like 1/2, right here, it's 1/2, the graph is now what? What term can I use to represent this graph here? What word? I think you had a hand again. Wider? Yeah, the graph is wider. Very good. The graph is wider. So we could say if A, and we're going to talk about this in a minute, is between 0 and 1 in this case, right? So if A is between 0 and 1 in this first case, the graph gets wider. Okay? It gets wider. Now, before we go on to the other side, we'll take a look in a minute. What happens in the third example down here at the bottom? Here's the parent function in blue. And then suddenly we're looking at the graph of 2x squared. And the graph, what happens now? Instead of getting wider, it gets what? What's the word instead of wider? Narrower. And this happens when the a value is bigger than 1 now. Narrower, or another word for narrow, is steeper. Okay, so you can say steeper as well. You have to do a lot of graphing on these without a calculator. So this kind of stuff you need to know how to do. Okay, you need to know what's going on here. Now, that holds true for the positive parabolas. What about this negative parabola down here at the bottom? Can somebody make some sort of a conjecture about the negative parabola down at the bottom down there?
It looks exactly the same.
Yeah. So negative 2 also makes it steeper, doesn't it? It just happens to flip it over, as Chris used the word reflection, or it just turns it around and makes it concave down. But the negative 2 is still steeper. So A could be bigger than 1 to be steeper, or narrower, whatever term you want to use. Okay? A could also be bigger than negative 1, but in the negative direction. So it's less than negative 1. But what we can say is the absolute value instead. And that will take into account that fact about the other side as well. Put absolute value over here. Okay? Make this absolute value, and then what this tells us is that if A is 5, it gets steeper. It gets really steep. If A is negative 5, it still gets steep, but it happens to be reflected also, but it's steep. So it doesn't matter whether it's positive or negative to affect the steepness. Now, the same thing goes about here. This portion right here. What we can do though, instead of writing it like this, and this is why I said hold off for a sec, we can write it like this. The absolute value of A is less than 1, which takes into account not only the positive fractions, but also what? Yeah, so if we had something like negative 1/2, here's what it would look like. I'm going to draw it on the bottom graph. God bless you. The yellow you're seeing on the bottom graph here is the parent function with a negative x squared right here. So if I had negative 1/2 x squared, it would look like this. Okay? It would still be wider because it's 1/2. This is again. It would still be wider because of the 1/2, but because it's negative, it gets reflected or it becomes concave down. So again, the A value what you're looking at is its absolute value to determine whether it's narrow or wider. Let's write a cliff note at the bottom then, please. So to determine whether a graph is narrower or wider, use the absolute value of n. So again, determining whether the graph is narrower or wider, use the absolute value of n. To determine if it's concave up or concave down, look at the sign of n. What do I mean by sign of n? Whether it's what? Ian? Yeah, positive or negative. One more fun fact, and you should have seen this yesterday. When when a equals 0, what happens?
The whole from the 0.
Yeah, because what's 0x squared just?
0.
Right, this just becomes y equals 0. Anything times 0 is 0. So when a is 0, you have the line y equals 0, which happens to be what?
0.
No, there's a line for it.
Along the x-axis.
Very good, Ryan. Well done today. Keep it up. It's the line along the x-axis here. Okay, that's the line y equals 0. So if a is 0, it's got no concavity. Think about it logically. Ready? Watch this, guys. And it's going to be tough for me to do this with my finger, but I'll show you on GeoGebra later. If I take my hands like this, and I look at concave up, if I stretch my fingers enough to look at the concavity, it doesn't become a flat line. This is concavity 0, until what happens? Concavity changes and becomes negative. So positive concavity, positive, positive, positive. No concavity, negative concavity, negative concavity. Okay?
Your hands aren't straight.
I'm trying to. It's tough to do that now. Okay? So you're looking at a graph that goes like this. If A is positive, if A is still positive but getting smaller, still positive, getting smaller, until A comes all the way to be 0, it's got no concavity. It's a flat line. Then A becomes negative. Then it becomes more negative. It gets steeper. It becomes more negative. It gets steeper. So these are all possible graphs of all those values we looked at. But y equals 0 is the flat line across the middle. Okay? Let's take a look at the next example to take a look at transformations. Or First, we're going to look at the vertical shifting of a graph, which occurs when the equation takes on the form y minus k equals ax squared. And we're going to make a conjecture based on what we see in our problem here. The box, these all got shifted for some reason with the program when it loaded. See this right here, guys? Take these three, please.
Blue, red, green.
And they're going to slide down accordingly. So the first one is the blue line, the second one is the red, the third one is the green. Is that clear? Okay, I don't know what happened. I'll fix that in the notes. So that should be shifted down. Anyhow, back to the problem itself. What we want to look at here is see that these graphs are all identical, except what's happened to them instead. It's been a normal graph like this, and what happened to it? Joe?
It moved up.
Yeah, and then the other one moved?
Up.
Start with the parent. Start with the parent in the middle. So they moved up or down, right? Up or down. Now, take a look. The red line is the y minus 3. That's this. I'm going to circle it in red. That's the red line in our diagram. So, look at the original form. Y minus k equals ax squared. So for this one, what is the value of k in this problem? What is k? Joe? Louder? 3. K is just 3. Is this clear by looking at the standard form, y minus k, and then you have y minus 3 going from there to there? Okay, the k gets its place taken by the number 3, so k is just 3. So when k was 3, the graph shifted where? From the origin, how far? Up how far, Joe? 3 units. You all see that? The original parent function was on the origin, the function y equals x squared. It shifted up 3 units because k was 3. So k dictates what? If we were to write this in words. K tells us the what? The what? Be careful. In this case it does. Yes, Ian. But generally speaking, what do we call it when we slide something up and down? Okay, that's good. That's a good term, the height of it. Or let's use the term vertical shift because we've been using that one. Okay, so the k value dictates the vertical shift. And notice when k is greater than 0, when it's positive, the graph shifts up. Look at the bottom example now, in green. So let's look at this green part right here. What is the k value in this part? When y plus 4 equals x squared, what is k?
-4.
Negative 4, because this should really be written like this. We all agree with me there? Isn't double negative a positive? So minus -4. So the standard form is y minus k, and this is y minus -4. So as Kate just said a minute ago, k is simply -4. And that caused the graph to shift what? Up or down? Down. How far, everybody? 4. It went down 4 units. So when k is greater than 0, it shifts up. But when k is less than 0, it shifts down. So those are our two conjectures in this problem. Questions on this part so far? We got 2 more to go. 2 more to go. Okay? We'll look at a horizontal shift, and then we'll look at an example where they're all shifted. We have a shift, we have a reflection, and we have a horizontal shift. So let's look at the next one. We're going to look at horizontal shifting now. And take a look at the standard form now. Instead of it being y minus k on the left side, we're looking at the x minus h on the right-hand side. And notice the x minus h is in parentheses.
There are phones flying out of the time.
The x minus h is in parentheses here. So what we have, and we notice here, is that our parent function is still on the origin, and the red function has shifted to the left 3 units. So what you notice for this problem here, we have this. What's the h value in this problem? What is h? Chris?
Is it -3?
Very good, Chris. Because this should really be written as like that. Remember, minus h, x minus h is the standard form. So h is -3, it takes the place of it. So h is -3, caused the graph to shift 3 units to the left, so the same rule applies, except this time, instead of shifting up and down, which way are we shifting? Left to right. So when h is negative, the graph shifts left. And then the green one shows us what? Right here. What conjecture can we make from that part? Chris?
When it's positive, it shifts to the right.
Good. Okay? And h is positive because here h is just 4. Remember, it's x minus h, so h is just 4. That's the h value. Okay? That's the h value right there. Okay? 4. So that 4 becomes h, and when h is positive, we see that it shifts to the right 4 units. Question so far. We looked at all these transformations individually. Let's put them together now and take a look at an example together. Okay, and I already have the graph up here because I want you to see what's going on, and we'll look at a graph we can do on our own, an example. But take a look at this example. So here's our example. Alright? Here's our example. And what we want to notice here for this example is that we have 2 kinds of shifts. We have a vertical shift and we have a horizontal shift. The vertical shift is identified from the -1. So what is k in this problem based on this? What is k in this problem? Kate? 1. Because again, it's y minus k, and then it's y minus 1. So k is taken its place by 1, has had its place taken by 1. And h, everybody, what's h? 2. So this tells me that there is a horizontal shift. So here's the original. There's a horizontal shift over 2 and up 1. And that's where the new vertex is going to be. And that's what we're seeing here. We see the shift over 2 and then up 1. And here's the vertex. So, what can I say about the vertex location? Is always going to be dictated by what? What will the vertex always be in variable form? The vertex should be equal to some coordinate always, and we can use variables to represent the vertex. Jared? Very good. Again, H is the 2, K is the 1, and notice the point here? Isn't this point 2, 1? Isn't that H, K? So H, K is always going to give me the vertex. Always, 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 always. Okay? The vertex. Now, draw in your axis of symmetry now, please. For this one. Okay, that red dashed line. What is the equation of that red dashed line? That vertical dashed red line. What is its equation? What? To what? X equals 2. Come on, guys. Vertical lines are x equals. Get that down. Now, what is the h value in this problem? What's the h value? Read it. 2. And this is x equals 2. So can we generalize about the axis of symmetry also? What statement can we make about the axis of symmetry? Kate? Yeah. X equals h always. Again, x equals 2 was my axis of symmetry. 2 came from the h value. The axis of symmetry will always be x equals h. The vertex is h, k. Is that okay? Are we good? Yes? For a quick second, you don't have to draw this, but let's imagine, if you will, let's imagine that the graph had a negative in front of it. So imagine if this had a negative in the front right here. Okay, there was a negative right in front there. What would happen to the graph? What's the only difference in this entire answer? Okay. Yeah, so you start at the vertex still, and you would draw the graph like this. Concave down. Okay? It'd be concave down. Chris, that's why I talked about the reflection idea. Because if you use the reflection and you reflect it over the x-axis, it's not going to work. So what you need to do in this case would be reflected over the line y equals 1. You see what I'm saying? See that reflection right there? The line y equals 1 is right here. Okay, that's the line you'd have to reflect it over. So you can think of it as a reflection, but it has to go over the line y equals whatever the k value turns out to be. Alright? Let's finish with an example. Let's finish with this example. And what I want you to do is start by identifying A, H, and K. Write down what you think is going to happen. But then, and again, sorry, let me go through this. Sorry. Identify A, H, and K. List the vertex. List the axis of symmetry. So go through all the identification stuff. But then what we're going to do is we're going to use a table of values today to make the graph look a little nicer. I am. So tomorrow, you guys don't have class. What you guys are going to do on Friday, though, is you're going to work on, remember the assignment that I gave you guys on Monday that you were to work on out of the textbook? Some of you finished. There were a few people that got close to the end. Some still have a few to go. You're going to finish this, and there's also a whole other worksheet. So if you finish this, and you want to work on the worksheet on Friday, get right into it. And if you finish that, you don't have homework over the weekend. But your homework, at the end of class on Friday, though, this needs to be turned in complete. Okay? So this needs to be done by the end of class on Friday. Okay, you'll have a sub, and then you'll work on the worksheet. The worksheet will be a bunch of examples like this, where you're going to have to graph parabolas in vertex form. And it's going to be just like the example we're doing now. Is that clear? Alright? Now, over the weekend, I've asked you guys not to do anything, but one thing I do want you to do, is just read 2 pages in your textbook. And I wrote that on Moodle, you'll see. Page 319 and 320. Alright? So, real quick, I'm just going to give this back to you so I don't forget. If this is completely done on Friday, what you're going to do is you're going to come in, you're going to work on your worksheet, the worksheet that the sub gives you, and if you finish that worksheet, you can turn it in and then read the 2 pages of the textbook. But it will probably take you the full period to do that. Okay? You don't really need to finish this in the next 2 days. If you have other work to do, do that, because you'll have time on Friday. The worksheet is not crazy long, but it should take you the period if you have this to do also. Is it complete? It's totally done? Oh, then I'll keep it down. If you're totally done with this, I'll keep it, guys. Yeah, this is being checked in.
My work is in the back.
Okay.
Not
You assume everything is graded always. So let's go into this now. The h value comes from in here, and it's really negative 3, because we have to think about this as x minus negative 3 inside of there. The y value is simply 2, the k value is simply 2, because it comes from right here, y minus k, so k is just 2, and this is x minus h, so h is negative 3. What's the a value? Ian? Negative 1. So tell me, Jared, something about this graph you know already just by looking at these three.
It's concave down with the vertex at negative 3, 2.
Awesome job. That's exactly what I want to hear. The vertex is negative 3, 2. We could even write the axis of symmetry, even though it's not needed right now. That's x equals negative 3. And it's concave down. Now, that doesn't really give me enough information to graph this. It just tells me a general idea. So I know the general shape will look like this. The vertex at negative 3, 2 is over here. 1, 2, 3, up 2. And it's definitely going to be concave down. And what we're going to do next week is talk about finding the intercepts and stuff. But for the sake of today and tomorrow, or today and Friday's work, what I want you to do is make a table around the axis of symmetry. For example here, you know the axis of symmetry is at negative 3, so make your table around there. So here's what your table is going to look like. So 2 below negative 3 and 2 above negative 3. So use negative 5 and negative 4. You know negative 3 is the vertex already. Then use negative 2 and negative 1. So pick values 2 to the right and 2 to the left of your axis of symmetry and plug them into the value of the function to get the y coordinates.
And should we simplify the equation if possible and then plug in the values? Or leave it as the form they give us?
It's up to you at that point. You can move so for example, you can move the k value over and then get the y, so you can add 2 to both sides and then plug in. That might be easier, Jared. Okay? The numbers you're going to get here are going to be negative 2, 1, 1, and negative 2. And if you do this right, notice the symmetry. Negative 2, 1, 1, negative 2. If you put it in the correct order and you work your way around the axis of symmetry, you'll see the symmetry in the y-coordinates as well because of the nature and the beauty of the graph and how it's symmetric. So in this problem, what you want to do is graph all these points. Okay? So let's go over to 5 and go down 2. Go over to 4 and go up 1. Go over to negative 3 and go up 2. There's our vertex. Go over to negative 2 and go up 1. Go over to negative 1 and go down 2. And notice, here's our vertex. It's concave down for sure. And the axis of symmetry goes right through the vertex. Are we good? Does this make sense? Are we clear? The notes for 7.5 are on Moodle. There's a lot more we're going to finish up with on Monday. You can read them if you'd like to. But your homework this weekend is to finish the worksheet you get on Friday, to read the pages in the textbook that I assign you. Listen, if you do both of those things, that's awesome. But do not give the sub a hard time. Okay? I don't even know who the sub is. I have no idea. All I know is this, guys. On Friday, when you're here, is talk about how we can use our intercepts to help us graph these quadratics. So we know the vertex already, and now we can find the intercepts to help us graph it. So remember, if you want to find the y-intercept, just set x equal to 0. Same as we did with linear functions, no different. If you want to find the x-intercepts, set y equal to 0. So you're simply just setting the opposite variable equal to 0. Now, notice when you set y equal to 0, you're going to have a quadratic you need to solve. So these are the roots of a quadratic. So they can be real and distinct, they can be real and repeated, or they can be imaginary. Remember the 3 types of roots based on the discriminant? Okay, so for the second part, it's going to be a little bit tougher. Now, if you remember, when the roots are, let me point here, when the roots are real and distinct, we had 2 different roots, and again, distinct meant different, right? But when they were real and repeated, we only had 1 root, and when they were imaginary, We had no real roots. Okay, no real roots. So I'm going to give you an easy way to remember this. All right? Pick a color. So for the first case, when the roots are real and distinct, it just simply means you're going to have two roots. And remember, what are roots really on a graph? What do roots show me on the graph again? The x-intercepts. So pick any 2 points along the x-axis, literally right now. Put 2 dots on the x-axis. Make sure they're different, not on top of each other. Put 2 x-intercepts on here, anywhere you want. And yours might look different than mine, don't worry. Just pick 2 spots to put x-intercepts. And there's no right or wrong answer at all. Alright, so let's say you picked a point here, and it doesn't have to be the same as me, and here. Okay? Yours might both be on the left side, they might both be on the right side, it does not matter. Okay? All that matters is this. When the roots are real and distinct, you're going to have 2 x-intercepts, which means that the parabola either opens like this through it, or like this. So one of your options is this. So that's what the parabola will look like with real and distinct if A is positive. But if A is negative, and the roots are real and distinct, you're going to have a parabola that looks like this. And again, we don't know how high up it's going to go or how low it's going to go yet, and we'll talk about that later. But when the roots are real and distinct, you can literally see both x-intercepts. Okay, Johnny?
So what about when it's like up and down, like down and up?
That has to do with the A value. So it could be either of these 2 graphs. That's what I'm trying to say.
Yeah.
Either of these 2 graphs are acceptable.
Yeah, but what happens when you get that?
That's a cubic function. That's x to the 3rd power. Yeah. And we'll talk about those later in the year, and they're called polynomial functions. Okay? So Johnny was talking about the cubic function when you have 3 roots. Okay, and that's x to the 3rd. Now when they're real and repeated, think about it this way. If you have a repeated root, it means draw a root anywhere. Pick another location somewhere. Just one though. Just one location. Now, if the other root is repeated, repeated means the same, right? So Nick, where's the next root going to be? If it's the same.
Like on the opposite side?
No, it's the same, literally.
Would it be on the same page?
Yeah, so it'd be like this, ready? There's the first root, and watch what I'm going to do. I'll color the next root in with a different shade of blue. Here's the second root, right on top of the first root. So they lie on top of each other. This is the scenario where you have a parabola that looks like this. It's tangent to the axis. It literally touches it once. And let me clear that up a little bit because it doesn't look tangent. Let me just make sure it's very clear. Okay, and again, what does tangent mean? Yeah, it means it just touches it once. So when you have a root that's repeated, it's not actually going through the axis and coming back around. Okay, it's not looking like this one where it goes through the axis. If it was real and distinct, it would go through the axis and maybe come back around. But this is real and repeated. It just touches once and comes back. So it literally gets up to the axis, it touches it, but then it turns back around. Now it could open up or it could open down based on the A value. So this graph also could have looked like this. Okay, and we're going to do a bunch of these examples today so you can see these. Okay, but when it's a real repeated root, and write this down please, we say it's tangent to the x-axis. Tangent to the x-axis. There's one last scenario. We use green for the last one. And the last scenario is when the roots are imaginary. Okay, when they're imaginary. When you're a kid, and maybe you have ever hear of imaginary friend. Little kids sometimes like, oh, I have an imaginary friend. Yeah, his name is whatever, and he speaks this language from another world. Little kids like to do that stuff. Imaginary means you can't really see it, right? Can't see it. So if you have imaginary roots, you can't see them. So what that means is that the parabola doesn't actually cross the axis. It's floating. So draw yourself a parabola like this. Or like this. Okay? That's the example of when they're imaginary roots. If you ever get roots and the I is in the answer, you don't actually have any x-intercepts. Because the roots are imaginary. They're not real. And remember, when we graph, we're graphing real things. So the roots for this parabola that's floating cannot be seen. They're imaginary. Or this parabola down here. This green one down at the bottom. Or this green one up top here. They're imaginary. Okay, they're imaginary. So those are the three scenarios we're going to talk about. When you have an imaginary roots, when you have a real repeated roots, or when you have real and distinct roots. The same exact scenarios as we had with the discriminant. Okay, Alejandro. This one down here, what makes it imaginary? The fact that it's not crossing the x-axis. Okay? So the red one was an example when the discriminant was greater than 0, if you remember, when they're real and distinct. The blue one, when they were real repeated, was when the discriminant equaled 0. And the green one, either one of them, was when the discriminant was negative, which caused imaginary roots. Okay, imaginary roots. So this is going to tie back into the quadratic formula eventually. Johnny.
So you could have it right out almost touching the x-axis and it's still be imaginary.
Yes. If it didn't, see how this d equals 0, the blue graph just touches the x-axis? If it were shifted up just a little bit, the top one, and it didn't touch, it would be imaginary roots. And that would be because the discriminant would be negative there. Okay? Let's look at an example. So for this example, what we're going to do is identify the vertex and axis of symmetry, and then look at the intercepts to help us graph it. So start by looking at H and K and A, same thing we did last time. And then after that, we'll look at the intercepts. Remember your standard form. Now, Erickson, tell me, here's H, and here's the number 2. Here's K, but here's the number 3. But the signs are a little bit off. Can you identify what H and K are?
K is -3 and H is 2.
Very good. And let's go through this. X minus 2 is replacing X minus H. So the H must be 2. Okay, the minus signs are like, it's like they cancel each other out in your head. They don't really, okay, but think of it that way. The H gets its place taken by the 2. But over here, the K gets its place taken by not a 3, but really a negative 3. Okay, because remember, this is really like saying y minus negative 3. Okay, that's what that's really saying up there. So the y minus K becomes y minus negative 3, so K is negative 3. So remember from last class, we quickly went through that, and you saw that in the video, that HK is the vertex. So there's our vertex. So already we know that we're going to be going over 2 and down 3. And that's going to be our vertex right there. Okay? Now, is the graph going to open up or down? Everybody, up or down? Up? 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 Okay. Why is it up, everyone? A is positive. Okay? A is 2. Right? A is 2 in this case. Now, does that mean it's going to be steeper or wider, God bless you, than a normal parabola because it's 2? God bless you. Steeper. It's like slope. Remember, when the slope goes up to like 3, 4, 5, the graph becomes very steep. When the slope is a fraction, it becomes very not steep. It becomes very flat, the graph. Okay? So a very steep graph here. But the next part is like, all right, I don't want to pick a table of points again. I want to think about what are my intercepts now. So find the y-intercept. The y-intercept should be easy to find. Just set x equal to 0. Okay, take a look. This is to find the y-intercept down here at the bottom. Just set x equal to 0. What's 0 minus 2?
0.
Negative 2.
Sorry.
Negative 2 squared?
What?
Negative 2 squared? 4 times 2? 8. Move the 3 over. 8 minus 3? 5. Now, this makes sense to me. You know why? Remember I said the graph's going to be really steep, isn't it? If this is your vertex, look how steep this graph is going to be. Everybody see what I'm saying now? How steep it is? Okay, if I were to trace my outline of what I think it'll look like this. It's going to be extremely steep, this graph. Remember, your y-intercept is a coordinate. It's not just 5. It's 0, 5. And I know the x is 0 because I set x equal to 0 here to give me the y-intercept. So the 0 for x is there, and then the 5 is the result of solving this equation here. Okay? So when you solve that, that's what you get for the y-intercept. The x-intercepts now. This is where we're going to have to look at our 3 cases. Either it's going to be real and distinct, real and repeated, or it's going to be imaginary. So let's take a look. To get the x-intercept, we set y to 0. Okay, so we take the original like this, and we set y equal to 0 to find the x-intercept. So we still have to solve for x now. But there's no need to FOIL it out and use the quadratic formula, because when it's in vertex form like this, just solve it like we've done in the past. Okay, the 0 plus 3 just becomes 3. Is that clear to everyone? I can get rid of the 0 plus right here, which becomes a 3. Divide by 2. Get rid of the square. Get rid of the square. How do I get rid of the square here? Square rooted. And then add 2. So these are my 2 x-intercepts here. Are they imaginary? Why are they not imaginary? What would cause a number to become imaginary if something is under the square root? If a negative. But see, look here. 3/2 is definitely positive. Sure, the answers are going to be a little messy. They're going to be irrational. We're going to get some decimals along the way. That's fine. But they're not imaginary. They're also not repeated because there's a plus or minus here, which tells me that the roots are going to be different. So if I wanted to find the 2 x-intercepts for this problem, okay, if I want to find the x-intercepts, one of them is 2 plus root 3 over 2. The other is 2 minus root 3 over 2. Go ahead and find the decimal representations of those. Estimate it to the nearest 10th, please. You know what? This is the one time I'm not going to ask you to do that, because when you graph, you're going to need to know what the decimal value is to graph it, right? So it doesn't actually matter to rationalize here. If the problem said find the x-intercepts, and it was a multiple choice, then and you had this as your answer, you probably would want to rationalize this portion because the multiple choice answers are like that. But for graphing purposes, there's no real need to, because now you can just get the decimal representations of these roots to then graph them. Okay? Nick?
Can I close the window a little bit?
Yeah, sure. What do you got for your roots here? You should be using your calculator to check this. Anybody got these? Erickson? Okay, so the nearest 10, 3.2. And x2? So, to the nearest 10th? Good. Okay, so 3.2 and 0.8. 3.2 and 0.8. So let's go ahead in our graph and find those. So again, the x-intercepts become this. We wanted to write them as coordinates, right? 3.2 and 0.8. And again, the y values for the x-intercept are zeros here. Okay, these are zeros both. Because remember, how do we get the x-intercept? We set y equal to 0 over here. Okay, we set y equal to 0. So let's go ahead and graph these. 3.2 and 0.8. Use green. There's 3. There's 4 out there. So here's 3.2. And here is 0.8. And look how perfectly they match up. They better match up, right? If they don't, if you got an answer of like -4 as an intercept, is that going to make sense to have a root out here? The graph would go like this. Whoop. That doesn't make any sense, right? To do that? It's got to be a parabola. So if we connect this, and what else can we do? We could think about the symmetry in a parabola. See this 5 for the y-intercept? Does everybody see that? Take a look. Draw your axis symmetry here, please. Remember, the axis symmetry always goes through the vertex. There's your axis symmetry. The line x equals 2. Okay, that comes from here, remember. The h value always gives you axis symmetry. Because of the axis symmetry, we can think of it this way. If I go over 2 units, boom, boom, I go up to 5. So if I go over 2 units this way, I should also go up to 5. So you could put another point up here. Again, symmetry, over 2, up 5, over 2, up 5. So put another point up here. Okay? And that's going to be the symmetry from the axis. And that symmetry point comes from the y-intercept. We just pretty much reflect it over the axis. And then you've got your parabola. Okay? So again, this kind of a problem, identifying the intercepts, really helps us. The y-intercept not only identifies it, but it gives us another point on the other side of the x, or the axis symmetry. And then the x-intercepts give us 2 other points. And now we've pretty much created enough to graph. It's no different than a table of values. You still have 1, 2, 3, 4, 5 points. Okay? You still have 5 points. Any questions on this one? So what are the steps? Identify what parts of the parabola.
Vertex.
What else?
The vertex.
What is the dashed line called?
The axis of symmetry.
Good. What are these called?
The roots.
Roots, good, or the x-intercepts. And then this is called the y-intercept. Okay? So when something is in vertex form, like seen here, those are the 4 steps we're going to use. Now, problems are going to vary along the way. Okay, problems will vary along the way. Let me see if I want to jump to number 4 or do number 3. Let me just look. We'll do number 3. We'll do number 3. Go ahead and write it down. Okay, go ahead and write it down. And what I want you to do is take about 3 minutes. I know it's quick, but 3 minutes to identify the vertex, the axis of symmetry, the y-intercept, and the x-intercepts. You don't have to graph it right away, but try on your own to identify this. Okay, to identify this. Now, what we're going to do here is we're going to see, we look at our standard form. H is, Erickson? Good. K? -2. Remember the standard form is y minus k equals a quantity x minus h squared. The a value is -1, which tells us it's going to open down. So the vertex, by default, remember, is h comma k. The axis of symmetry just goes right through the h value of the vertex, so it's x equals -3. Okay? So this is what we know already. Again, we always take that value. It's always going to be the same. Always, always, always. Okay, these two will always be the same. At this point, we can find our y-intercept by setting x equal to 0. What do you get for the y-intercept when you set x equal to 0 here?
11.
You got 3 squared is 9, and then subtract 2, 7? 7 or 11? 11? Mr. Howell's going crazy? Oh, perfect. -11. Right? -11. Right? People?
Wait, so when you
We square the 3 to get 9, but it's negative of that. So this is going to be... I got no room. Okay, like that. So the y-intercept is 0, -11. All right. What do the x-intercepts turn out to be here?
3 plus or minus I root 2.
3 plus or minus I root 2. Now, I have -3 plus or minus I root 2. Be careful. That's all right. But the idea is that, what kind of roots are they? Imaginary. So are they going to show up in the graph? So immediately, whenever you're going to get imaginary roots, it doesn't even matter really. Once you realize that they're imaginary, if you get a negative under the radical, you can stop for graphing purposes. That make sense? There's no need to waste your time. If at one point in time, because here's what you're going to get. Let me show you what I mean. This is how you get the x-intercepts, right? You set y equal to 0 right here. Once you move the negative over, you're going to get this. And then when you take the square root, what's going to happen? Square root of negative becomes I automatically, right? So you could just stop right here and say imaginary roots, because they're not going to help you graph it. Whenever the imaginary roots aren't helpful, and whenever the roots aren't helpful to graph, it's not worth even going through it, because you're going to get this as your next step. Okay? So just stop there and just say imaginary roots, because they're useless when it comes to graphing. Right? Alright. Now the issue when it comes to these graphs with imaginary answers, it's tough to graph them. So let's go ahead and take a look at now what the graph would look like. The vertex is -3, -2. The y-intercept is all the way down at -11, right? So maybe you want to go by 2s along the y-axis. I can move. Can't move it, never mind. Let's go by 1s, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's the y-intercept. Here's the vertex. Here's the axis of symmetry. Remember, it always goes through the vertex. So I know there'll be another point over here now, right? Take a look. If I go and think about this, I know this point here will be reversed over here because the symmetry of the parabola. I know it opens down because it's concave down. So I can reflect this over. 3 units over. So I can go additional 3 units. And then go down to -11. Put that point there. But that, that's a really rough estimate of the graph. So if you would like to, when you're graphing, you can pick one of these 2 points, -2 or -1, or one of these two points, -4, -5, and just pick those values and put them in a quick table, run them through to find those coordinates. So if you want to plug in -2, you'll get -3. If you run -2 through the equation, you'll get -3. And if you run -4 through the equation, you'll also get -3 because of symmetry. So if you want to do that, you can put that point there and that point there. Okay? Look like that. Your homework tonight will be on Moodle. If you want to write it down, you can write it down now. It's 3 through 30, multiples of 3. Okay? And number 31. There's a 4th example I'll record. Okay, I'll record the 4th example. If you want to watch it tonight, you can. You could also just read it on Moodle. It might help you for one of your examples for the homework. Okay, but this is it for graphing really for this section. 30. Okay, so for a problem like this, we want to find the equation of a quadratic in vertex form having a certain vertex and containing a certain point. So right away, let's start by thinking about this. Well, the vertex is always h comma k. So here's h, and here's k. So we could start by plugging those into the original equation of the standard form of a vertex form for quadratic by writing it like follows. And then this will simply look like this. Now, from this point, we could say to ourselves, well, we need to know what that a value is. And it's tough to figure out a. And the first thing you can think about is, well, let's see what the graph looks like, get an idea. The vertex is 2, -4, that's like here. And then a 5, 14 is somewhere up here. So it's definitely going to look something like this. Okay? So a is going to definitely be positive, we know that. But the question is, what is the a value? And if we think about this, though, if the parabola contains this point, it means that it's on the parabola. So it must satisfy this equation. So we can take 5, 14 and plug 5 in for x, and 14 in for y, since that's x comma y, and solve for a. And then 5 minus 2 squared is really 3 squared, which is 9. And this is 18. So a is simply 2. So our final answer is the same as this line right here, but with the 2 in for a. 3, and then number 31.
What's that?
7, 5.